And thank you for attending our Capital Essentials Design and Harness Process Overview webinar today. For those of you that aren't aware, Siemens has rebranded VeSys Electrical Design to Capital Essentials. So if you have some familiarity with VeSys, this workflow may look familiar to you. First, before we get started, I wanted to quickly remind you that we're consistently adding new Solid Edge and NX, CAD, CAM, and electrical content to our Prolim YouTube page. If you aren't already, go ahead and give us a follow on our YouTube channel so you get access to all this new content when it's dropped. So first, let's take a minute to imagine a scenario. You're an engineer responsible for working on one of the harness designs in this cool truck. And after months of hard work going into the production and it's now on the road, you probably feel pretty great about yourself, right? Let's say a few months later that they are all then recalled because of an issue that can be tracked back to the harness design that you were responsible for. Probably not feeling so great anymore. This is obviously a terrible situation for the individual engineers responsible, but also terrible for the company as a whole when you take into account the financial repercussions, time it takes to resolve the issue, and then the damage to the brand image. This is essentially the worst case scenario that highlights the importance of getting your designs correct the very first time. Unfortunately, this is one of the potential side effects of a common industry trend. Electrical content is always increasing regardless of the industry and application. This increases the cost to do the initial design as well as manufacture the harness, increases the overall design time due to complexity, and similarly, every time something new is added to the design, the chance of inducing an error comes along with it. With our tools, we attempt to address these issues through the use of automation, collaboration, and verification. The overall goal here is to reduce the design costs, design cycles, and the risk to avoid the types of disaster scenarios like the one that we just highlighted. So for this presentation, we'll walk through this small tractor design. The wiring and harness designs are partially complete, so the first step for us will be to finish off the wiring design. Next, we'll then perform an analysis to verify the changes we made. And then we'll synchronize our wiring and harness designs and perform some details on the harness itself. And then finally, we'll utilize automation to select the appropriate part numbers for our harness and then generate a couple of reports. So we'll start by updating the wiring design. First, we want to update the style sets, and this will add to the circuitry and connectors for the brake lights. We will also add a multi-core and overbraid to our instrumentation diagram. Here in our lighting diagram for our tractor design, we need to update it by adding new brake lights. But before we do that, we'll also change the style sets. The current color scheme is a little on the distracting side. We can do this via the Style Sets command dialog. And that will allow us to update the look and feel of our diagrams without changing any of the connectivity or needing to recreate anything. First, we will disable the names of our wires that are currently just cluttering up our design. We'll also set the colors of our wires back to default. We'll make our devices black, and then we'll set our connectors to a custom color. Once we are satisfied with our selections, we can then apply the style sets across the diagram, all in one go. Making things a little easier on our eyes, that's for sure. Next, we'll create the circuitry for our new brake light system. Since it's similar to the other lights in our system we already have pre-configured here, we'll go ahead and just reuse this data to speed up the design process. By copying elements, we bring over the library part assignments, as well as any properties that may have been assigned. Again, saving us valuable design time. Now all we need to do is add another additional switch as our brake lights are independent of the light select. We'll go ahead and add a few wires to connect the switch to the system. And then next we'll want to go ahead and rename our devices and connectors by giving them more meaningful names. We'll go ahead and start with the resistor, and we'll call this R5. We'll also update its value, which comes into play when when running the analysis. For our switch, we'll call it brake light switch. And we'll also assign a library part. By doing this, we can utilize some automation to generate the appropriate harness connectors for this device. So now that that part is assigned, we can then use the generate harness connectors command to automatically create the appropriate connections. If we go back and look at this in our library part assignment really quick, we can see that there's an additional part number assigned for its connectors. So by running the generate harness connectors, not only did the connectors get generated on the diagram, but the appropriate library part was automatically assigned. This helps cut down on the human error and speed up the design process. While we're at it, we'll go ahead and rename the connectors, making them a little easier to pass over to the harness. And next, we'll update the names of our left and right brake lights. As you can see, we can do that right here in the graphical window without going to the properties, as well as our connectors. Next, we'll go ahead and create a note that describes the behavior of our light switch. So for position 1, all of our lights should be powered off. For position 2, only our warning lights should be powered. Position 3, warning lights and power lights should be powered. Forgive my spelling. And for position 4, our front and middle lights should be powered. And then for position 5, we'll just leave this in A for now. We can then associate all the relative objects to this note, so it's easier to locate in the design. Now we can select the lights controlled by the light select switch, the light select switch itself, and the diagram that it's associated to. Next, we'll make one final update. We will add the multi-core and an overbraid to our instrumentation diagram. We can do this very quickly via the quick actions, which use a default multi-core and overbraid definition that allows some simplification to adding them to the design. With those in place, now we'll go ahead and pass it off to the team member to perform a quick analysis on our system for verification that the design functions as intended. So in this portion of the demo, we touched on a few of the features that help boost your productivity. Style sets enable you to quickly update the graphical representation of your designs to meet the corporate or custom standards you may have. Generate harness connectors make connector assignments significantly faster and less error prone by utilizing your parts library. Then the quick add actions simplify the multi-core and overbraid creations. Now that the wiring design has been updated, we need to perform analysis to verify the lighting circuit is behaving as intended. We will assume the role of a team member rather than the original designer to utilize some of the collaborative functionality as well. First, we will use qualitative analysis to find our connectivity issues, and then record the issues via comments for the original designer to correct. Then we'll perform a numerical analysis and correct any additional issues that we may find. Back in our lighting diagram, the first thing we'll need to do is open up the note that the designer left for us, looking for the behavior that we are looking to verify. For our light select switch, position 1 should have all of our powered lights off. For position 2, only warning lights should be powered. Position 3, only warning lights and front lights should be powered. Position 4, only front and middle lights should be powered. And in our case, position 5, not being used. We can use the associated objects to better understand which elements are associated to the list for instruction. This helps us verify the items to be validated and using analysis. Once we've confirmed our information, we can start our analysis via the Analysis tab. The color of the diagram will update to show any issues with the design, as well as the flow of the current direction. In this case, it's cyan to tell us that the design has no current flow for the particular diagram. Since both of our switches are in the open position and no path to ground, that's to be expected. We can control the switch position via the Analysis tab, as you see here. First, we will try to close the brake light switch positions or change them to closed. It appears we're still not getting any current. So next, we'll cycle through the light select positions to see if we get any power. Still no power. So this could indicate that there's a problem with the design, but I think we can dig a little deeper. So here we can see there's a power distribution cross-reference. We can quickly jump into the cross-reference to take us back into that diagram. Here we can see that we do have power in our design, as indicated by the green flow lines, and also including the arrow directions. It appears we are losing connectivity at the ignition switch. In addition to changing positions of components in the Analysis tab, we can also do so by hovering over the switch in the design itself to display the inputs. Our ignition switch is set to position 1, or open. This might be why we aren't getting power to our lighting system. If we close the switch, the analysis will update automatically in real time to show us the changes to our design. Once we change to green, here we can see that we now have current going into our lighting diagram. So now if we switch back over to our lighting diagram, we can see that we now have current flowing. Now that we have confirmed our system is capable of receiving power, we can continue on with our simulation. Looking back at our light select behavior note left by our designer, we can cycle through our power switch positions to confirm they are working as intended. Position 2 only indicates warning lights as it's green. Position 3 looks like we might have our first issue. Our warning lights aren't receiving any power. So position 4, 5, looks like nothing is powered as it should be. So let's go ahead and take a closer look at position 3 and 4 to see if we can figure out what the issue might be. So at a closer look, we can see that position 3A of our switch goes to our front lights, and position 3B also going to our front lights. So it appears we have no connection to our warning lights as intended by the designer. So this particular state can't be satisfied. Looking at position 4, connection 4B is going to our middle lights as intended, and then position 4A is going to our warning lights. So it looks like in this particular wire should be going to our front lights. So I think our overall situation is that we have two wires going to the wrong connection points. This fix, in this case, we can just swap the two wires. So we'll go ahead and leave a quick note for the designer. And we'll go ahead and associate the two lines that we're referring to. At this point, we will reassume the role as the engineer. Let's review the comment that the analyst left for us. Here we can select the associated objects left in the comments to quickly locate them, the items in question. This is an easy fix using the Manage Connections command. Locating the wires in question, we can quickly swap the connections. And just like that, the analysis updates and confirms that we now have connections as intended. Let's leave a comment back to our analyst that the design has been updated and the issue is resolved. This created a digital thread of communication across teams for future reference. A thread that might easily get overlooked or missed in the common email communications. Now that our issues are fixed, we can continue our analysis for the rest of the system. Let's quickly cycle through our switch positions to confirm all positions are operating as intended. We'll go ahead and stop this simulation, and now we'll go ahead and select the numeric simulation. This analysis type takes into account wire cross-sectional area and resistance. So it provides some additional level of detail that quantitative doesn't. So for example, if we hover over a wire, we now get a pop-up with additional information, such as the rated max amperage, current, voltage, and resistance values. Depending on the element that we hover over, we are presented with relevant information. The brake light lamp even shows a lit condition, as we can see here as yes. So not only does it tell us that we have power, but if we have enough power for it to function correctly. So now we can pass through our lights in our system to verify proper connectivity. Everything seems to be lit. So for position 3, we can see our lights maybe are not meeting our proper voltage. So when we hover over, we can see that that lit condition is not being met. So if we look at our analysis output window, we can see that we actually have a blown fuse. So let's jump back into our power distribution diagram. And we can now see that we have a yellow indicator for our fuse symbol, which indicates failure. If we hover over the fuse, we can see that there is a 10 amp fuse configured. We can also see at the bottom the suggested rating should be 25 amp. We will assume we know all 3 of these fuses should be a 30 amp fuse. So we can quickly change the associated part number to this fuse to change to a 30 amp fuse. We'll go ahead and filter by fuse. And we'll select our 30 amp fuse from our parts list. So now that it's been updated, we can now see that our fuse blown warning is gone and the color has changed from yellow to green. So let's go ahead and jump back over into our lighting diagram again. Hover over, and now we can see that the lit condition is now being met for all of our lights. So let's look at position 4. We will review our last position to validate that all of our lights in this position are working properly as well. But it looks like we might have a potential issue with one of our wires. This magenta color doesn't necessarily indicate a failure, but what it does tell us is that the current of a particular wire is over its rated value and approaching its maximum rating. So in this case, we will up the wire spec that can handle that current. Once the simulation reruns, so now that we can see that the magenta color is gone and replaced with the green flow indication, and we can also see the current as well within the rated value. So at this point, we have finished our analysis for our wiring diagram and ready to pass it off to the harness team for synchronization. In this portion of the demo, we demonstrated how analysis can be used to achieve better insight into a circuit's behavior. Analysis also enables you to find and fix issues early in the design process and avoiding propagating design errors downstream, where they become much more difficult to detect and significantly more costly to correct. We also highlighted some of the collaboration functionality via comments and notes, which is valuable in supporting team-based design environments, allowing you to document important design information within the tool itself. So it's easier to keep track and enables you to utilize the information interactively via cross-probing to make communication much clearer. To propagate our changes that we made to our wiring design to the harness design, we'll need to synchronize the two. First, we will update some of the attributes for our new content we added to prepare it for synchronization. And then we'll move to the newly added content to correct the locations on the harness and make any minor changes to the topology. And then finally, we'll update our tables to display the additional information that we recently added. First, we'll open up our wiring harness design. Here we can see that a majority of our connectors have already been placed, coming from a previous synchronization run, but now we need to synchronize again to bring in our recent changes that we made to our wiring design. Notice our naming of the primary harness. This will come into play here in the next few steps. There is one last thing we need to do before performing our synchronization. We need to assign the harness attribute. If we look at the brake lights, we see that they already have the harness attribute already set in the value of primary harness. That's because we copied them from the middle lights, which were already part of our harness, which means that all we need to do is add this content to the elements that were outside of the copy-paste function. We'll start by adding it to the wires, and then the brake light switch connectors and the brake light switch itself. A quick save and close, and now we're ready to synchronize. Upon synchronization, we can see that our newly added connectors for our brake lights, as well as our brake light switch, along with a few splices. The next step is to add these components to their appropriate locations on the harness. We can simply do that by moving them. Over a particular bundle, using the quick access grab handles, we'll go ahead and add a bin to our brake light bundle and reposition them a little further down the harness. And we'll go ahead and do that for the other side as well. Quick and easy. We'll go ahead and apply the style, and then the connectors will automatically reorientate for us. So next we'll take a look at the tables in our design. At the top here, we have a simple from-to wire connectivity table that automatically updates as we perform synchronization. So here we can see our newly added connectors for our brake lights, the switches, the splices, even the multi-cores that were performed before synchronization. Over to the left of our diagram, we have a table listing all of our connectors contained in our harness. And then we have these individual wire tables for each one of the connectors as well. All of these tables are configured in terms of what information we want to show and how they appear. This is all controlled via the styling. We'll make a quick adjustment to the columns of our wire tables. We'll turn on wire part numbers, as well as the terminal part numbers by making them visible. Upon updating, we can see our tables now reflect those changes. We can also manually adjust the placement of our information to better communicate our design intent. In this portion of the demo, we showed how simple it is to pass change between your wiring and harness designs to ensure that they are always in sync with each other. We also highlighted bundle manipulation via the grab handles, and then table customizations via the styling, both of which help keep your design clean and concise, giving you full control over how your harness designs are presented. Finally, let's take a look at generating some reports for our designs. Before we get started generating reports for our harness design, we have to select the appropriate part numbers for our wires and cavity components. This is a very quick and easy process using some automation. One more thing we can do, for the sake of reporting, is calculating our wire lengths. We can also automate to select the appropriate cavity connectors for our part numbers. We can also use Cavity Component Manager to select the parts on a case-by-case basis for each connector. Or we can use the part select in this case to select all of them at once for every connector in the design. With our library parts assigned, we can go ahead and select reports from the reports dropdown to start generating reports. We'll go ahead and use the pre-configured complete BOM selection. And here we can see that a very detailed bill of material pulled directly from the most up-to-date data in our design. No need to organize, format, or pull any data in ourselves. We can save these reports as HTML formats or print them for future reference. In addition to using pre-configured reports, it's also easy to create our very own custom reports as needed. For this example, we'll go ahead and do another simple from-to report for our wires. We'll add the part name for the first column. We'll do the part number for the second, and then from and to for our last two columns. So now we'll go ahead and give this report a name so it can be saved and reused for future designs. Then once that report has been saved, you can find it on the drop-down reports for easy access. There it is. So in this portion of the demo, we showed how automation can be used to streamline part selection, saving additional time, and further reducing the risk of error. We also demonstrated how simple it is to generate reports and even customize them to meet your company's needs. Capital Essentials provides functionality that helps engineers deliver rapid, right first time, error-free electrical and harness designs. Through automation, analysis, and a plethora of other time-saving features, it allows design teams to put their effort where it counts, in innovation. At this time, we'll take any questions that you may have. And if you don't have any questions at this time, feel free to direct any future questions that you may have to the contact information you see below here. Thank you and have a great day.